quiet here. No, we're just like kind of dying down.
All right, folks, thank you so much for being here today and welcome. You all got very quiet very fast, like in record time. When I said like a 2-minute warning, I literally meant 2 minutes and then it was just like 30 seconds and nope, you're sitting down, so cool. How many of you are visiting Galvanize for the first time? Oh my gosh, hi, welcome everybody, cool. Actually you, that's amazing. Wow. Okay, well let me introduce Galvanize to you. For those of you that don't know, Galvanize is a learning center for technology. It's our mission to make technology accessible to everybody with like the determination and the grit to succeed. And our job is to empower people to change the world through tech. And so I'm really excited to present what you're about to see today. And for those of you who don't know me, my name is Jenny Engard. I'm the Student Success Manager at Galvanize. So my role here is to shepherd these amazing humans through this program, both in a psychological and mental capacity, and also to kind of be like the cruise ship director behind the scenes to make sure everything is running smoothly. So I'm really, really excited to present these folks to you today. So just a quick rundown of what to expect. We're going to be having 8 presentations of about 3 minutes each with a 3-minute Q&A with our panelists. Hold your applause until after the panelist Q&A is over. And then after 8 presentations, we'll be going into intermission for 10 minutes, and then we'll be coming back and having the final 8 presentations. After that, we're going to be having a happy hour. We totally encourage you to stay behind, have some drinks, have some lovely food and beverages, and get to know some of these amazing people that you just saw deliver the culmination of their hard work. With that being said, I'm going to pass this off to Kara, who's going to introduce our panelists, and then we'll introduce Carrie, who is going to introduce this cohort to you. So again, welcome so much. Welcome to Galvanize, Carrie. Kara, I'll let you take it away.
Hi, I'm Kara. I've probably met most of you in here, and if I haven't met you, hi, I'm Kara. So basically, I'm the Partner Relations Manager here. I work on the careers team. My primary goal is to really connect our graduates with awesome job opportunities once they complete our program here. But part of something that I have the privilege of doing is hosting and inviting our amazing panelists here who are going to engage our student presenters. So I'm just going to pass along the mic to each panelist and then have you introduce yourself so that our audience can get to know you better.
Thank you, Kara. And thank you, everybody. I'm Alex Jesus. I work at Salesforce. We have a team that works on activity data. And I'll cover that in a minute. I've been in the industry for almost 20 years. Started when AI was expert system, right? So top to bottom, right? That's bottoms up. Back then studied prologue, theory of languages, and graph and whatnot. All of the stuff that's still today. Salesforce does a lot of work running the machine learning. You might have heard some of the initiatives under Einstein. So we have offices in Palo Alto, office obviously in San Francisco. So a lot of the Einstein is actually being over there. We have many types of applications, positions. We have a lot of analytics. We have a lot of applied data science, data engineering, research work also. My team specifically is focusing on communications data. So we have essentially activity data from customers, like meetings, emails, phone calls, and we can use that information to derive your intelligence and services. For instance, we're capable of looking at the content of the email, looking at what the competitors are being mentioned, when pricing are being discussed. Eventually, we provide direct services to the users for that. There's no communication channel we have. But also it will fit many higher level apps and models, like for instance, if you want to look at opportunity scoring, figuring out what opportunities are the most likely to close, you can start using communication data. And as you can imagine, looking at the number of meetings, emails, what's going on within there, eventually you will really reinforce the models, and then at some point you can start looking for patterns and what are the good things people are doing and so forth. So in my team, it's really more applied data science. So it's a combination of like data science with engineering. We use a lot of data, so we work in a platform like Spark and Scala. And on one side, we do a lot of modeling. So essentially doing a classifier, modeling for the content of the emails. And we also do stuff that's a bit more deterministic using graph, creating activity graphs, so having not just the text of the emails, but also the context we can do services and process connection, and we can determine if you have somebody external who can tell you who's the best person, for instance, for reaching out. That you can connect to, using an internal, for whatever it is. And we use that data also for reinforcing models, so I think that takes the context and it's kind of feedback loop.
Hello everyone, my name is Julia Immersive. I'm the Director of Data Science at Fitbit, and I have the pleasure of working with really amazing data sets, tens of millions of users, active users, and billions of nights of sleep, a lot of physical activity data, and with the hopes of using data science to help them live healthier lives, help them move more, eat better, and sleep better, and have less stress in their lives. I'm looking forward to hearing all the presentations today.
Hello, my name is Jeremy. I work for Allstate. I'm a data scientist, and now we're down in Menlo Park. Our research group is. We have a group of 300 to 400 people worldwide working on data science and data analytics. Some of our cool problems that our department tackles are, of course, connected cars for insurance. That's a big area of research right now. Of course, self-driving cars are the future. How are we going to insure them, et cetera, et cetera. Lots of other good stuff. I work directly with agency success, so deploying our predictive models to our agents directly and helping them meet their goals, et cetera, et cetera. Other than that, I am from the great state of Minnesota. Go Vikings. And it's a real pleasure to be here today. So I'm looking forward to the presentations.
Hi everybody, my name is Shruti. I'm the co-founder and VP of Data Science at a startup called Embody VR. So we are an audio technology company. We use a lot of image processing and machine vision to provide an immersive sensory auditory experience. We're at the moment 10 people, well, a very small team based out of Redwood City. And I look after the infrastructure, algorithm development, and getting a lot of machine learning scientists on board to join with us. We're doing a lot of research into feature extraction from images, videos, and 3D scans. So if you're interested in the space, please get in touch with me.
We can just have a round of applause for our panelists. Thank you so much. And now I pass it off to Carrie, our lead instructor.
Hi everybody, my name's Carrie. I was introduced, I'm the lead instructor for this cohort. So I have the pleasure of being able to introduce to you all of my students' projects, not one at a time obviously, but in the context that I can tell you a little bit about what they've been doing for the past few weeks and how they got from being students, walking into our front doors, what was it, like 11 weeks ago, to being able to stand up in front of you here in a few minutes and give you really elaborate presentations about some very hard data science problems. So yeah, in the Data Science Immersive here, as we call it DSI, we take a group of 20 or so students and teach them a bunch about machine learning for 8 weeks. And then they get thrown into the deep end, so to speak, and told, yeah, no, go sign some data or something, right? We give them a little more structure than that. But they spend 2.5 weeks working on a project in their design with our supervision and kind of gentle hand guiding them. And then they're off to practicing presentations, which is what we've been doing this week, culminating in today, where they get to knock your socks off with the stuff that they've been working on. So, I just want to take a moment and say to all my students, I'm extraordinarily proud of everything you guys have done. I'm just super excited to begin to introduce you guys today. So, thank you so much for all the hard work you've done. And everybody else who's here that I don't know, thank you for attending and checking out what they've been working on. Panelists, thank you for coming and all the awesome questions you're going to have for them. So, with that, I'm going to open it up with Lucia.
Good. Hi everyone, my name is Christina Norton. For my project, I focused on energy demand forecasting. Motivation for this problem is that energy demand forecasting is essential for the knowledge of distributed energy resources such as solar plus storage. In order for smart energy systems to make the correct dispatch decision at a given point in time, it's essential to have knowledge about future energy demand. Therefore, I built out a data analysis pipeline, which allows the user to compare 4 different forecasting models, and also built out capabilities for hour-ahead and day-ahead forecasting. For this project, I was working with 5-minute interval energy demand data from several commercial and industrial facilities across Accra in Ghana. And I also suspected that temperature would have an impact on energy demand, and therefore brought in weather data from the NASA MERA-2 dataset, which is available at hourly intervals. So in order to approach the problem incrementally, I started off by defining 2 baseline models. The first one is the baseline previous, which just forecasts the energy demand from the previous time step. The second one is the baseline average, which forecasts the energy demand, or the average energy demand for that time interval. And in order to build upon these, I looked into SARIMA models. But first, I considered just the basic SARIMA model, and then built upon that with the SARIMAX model, finally setting on dummies for a weekday or not, and temperature as the exogenous variables. So these are the summarized results of my day-ahead forecasts. What we're looking at here is the relative cross-validated RMSE for the 4 different models, which is being conducted across 6 different facilities in Accra. And as you can tell, the SARIMAX model tends to outperform the other models. And on the right-hand side here, we just have some example forecasts from the 4 different models across a single facility. And on the bottom here in red is the SARIMAX model performing the best. These are the similar results for the hour-ahead forecast, and one of the differences that we see here is that the SARIMA and the SARIMAX model kind of perform comparatively, with the SARIMA tending to do slightly better. And again, we have a similar plot showing the forecast predictions for the 4 different models, with the SARIMA performing best. This is on an hourly basis. So some interesting observations I found here that bringing in the exogenous variables had more of an impact on the day-ahead forecasts rather than the hour-ahead forecasts. Some reasons I thought of this were that the facilities could react slowly to temperature changes, or the fact that the city average temperature does not contain enough signal to look at hourly fluctuations. Furthermore, the baseline average model performs comparatively to the SARIMA model for facilities with very consistent energy demand. Looking closely into this, I noticed that given that the SARIMA model works on lagged variables, if there's a small disturbance, that disturbance is propagated forwards and could cause departure from the signal. So further work I'd like to do is tune the model for multi-step forecasting. So rather than just looking at a single day or a single hour ahead, looking several time steps in front. Second is incorporating the baseline average as an exogenous variable in the SARIMAX model, considering that it performed particularly well on facilities with consistent energy demand. And then finally, continue looking into long, short-term memory recurrent neural network models. These tend to perform very well for forecasting problems, and I built a basic model which performed comparatively with the SARIMA model on the test set. So I think it warrants further investigation and proper cross-validation. Thank you for listening. Again, my name is Rosina Norton. If you've got any questions, I'm happy to take them.
What is the model granularity? Is it at the facility level or the consumer level?
At the facility level. So this data comes from behind the meter real-time sensors, which are measuring voltage and current on each of the phases of the facility.
And so how many models did you end up building?
So I built 4 different models for 6 different facilities.
Oh, just
across different. So I took a selection from a range of different the facility, what they do. So I looked at hotels, offices, mining, processing, and kind of looked at the differences which occurred in the different facilities.
If you were to work for a utilities company and have to scale this up so that you'll be able to run your model for millions of households or businesses, what would be a good way to accomplish that?
Sorry, I didn't quite understand your question.
What would be a great way to scale the operations so that you'll be able to build models for millions and millions of households?
Yeah, so the way that I envision this working with the company that I work with, which could be scaled in a similar way, is that the data is measured real time and sent wirelessly to the to the utility or to the company, and all my models were set up to run on an EC2 instance on AWS with the data kept in an S3 bucket, and therefore this could be set up to run at intervals in order to train the models, and then it could predict at every single interval that you would need it to move forwards.
Sorry if you mentioned this already, but what training period did you use for those models?
Sorry.
How much time did you use when you trained
Yes,
those models?
so it varied for each facility. Some of them range from having a year's worth of data to a minimum of 3 months. And in each case, I did like a cross-validated time series training, where I split the data in half and then incrementally grew the data. And at each time doing a single step ahead forecast and then taking the RMSE of all the forecasts as the cross-validated performance.
Great. And then you mentioned briefly that you would maybe have something that auto retrains as time goes on. What interval would you recommend retraining and why?
Yeah, so I think it would depend on what kind of forecasting you're trying to do and facilities, their operation. So for example, one site which I found quite interesting was a university that I worked with. And depending on like the term time or whether it was not term time, they had different energy demands. So therefore, depending on the facility and how their energy usage is likely to change throughout different months, then I think you would need different retraining periods to capture any changes that occurred in recent weeks.
Yeah, I was going to ask you about that. So you get a few months per facility, but did you end up beating the deadline? It was even 5 minutes, every 5 minutes, right? But what else did you do for like, day of the week, months,
Yeah.
special, occasions and stuff like that?
So there was a number of things I did for that. In this Arima model itself, the S actually stands for seasonal, which kind of indicates over what kind of periods do we see the data varying. So for the day ahead forecasting, I had a season of 7 because we would see weekly trends in the data. And for the hour ahead, I had a season of a day because we go up and down every day. But also in the Saramax model, one of the exogenous variables was a dummy for a weekday or a weekend. So in the hour ahead forecasts where we can have the weekly season, bringing in that exogenous variable as a dummy for weekday or not allows the model to learn the differences between a weekday's load and a weekend's load. Thank you.
So hello everybody, my name is Jeremy Gosvan, and I'm going to present you Sneakit, Sneaker Recognizer app I just made. So just for you to know, I am a really big sneaker addict. I have more than 50, 60 pairs. So sneakers are everywhere, but nobody is really like a sneaker addict. And we never wanted to ask a stranger in the street about the sneakers because we thought they were cool. This problem got me into sneakers 6-7 years ago, when I basically spent more than 3 days online to look for a specific pair. So I asked myself, how can machine learning solve this problem in this context? And first, is it possible to recognize the sneakers with only 1-2 pictures? Yes, of course it is. I just made it. And can we make it easy for everyone to use? Well, it seems so things to happen. And what was required? As you might expect, some neural networks, a lot of sneaker images, and an easy access smartphone application. So now what's data? How did I get my data? So basically, I scrub Google Images and include IDs for every colorway of the specific model. The colorway is basically a color of the specific model. So how much data? So basically, I went for 10 colorway for every model. Every model, basically I went for 12 models divided into 4 brands. So around 23,000 images total divided into training, testing, and validation sets. So can you recognize every sneakers? In theory, it can. But for a starting point, we intended to go with 4 brands and then 3 models each. So now about the modeling. I also decided to apply transfer learning using the BTD16 architecture using the Keras library with some data notation. And what my neural network learned about this new data, I basically fine-tune my model, removing the top layer, adding some extra layers, and also and further, I just throw some extra layers. So for the starting point, I decided to go with one model running an all sneakers model. And the thing is, as you might expect, I had like a really good accuracy, close to 92%, but I had some drawbacks. First, it wasn't really able to categorize and classify sneakers, even taking related to the brand. And then as the number of models, of sneakers models increased, the accuracy went down. So basically what I ended with was one model categorizing brand first, and then passing this result to some models, some neural networks model, to categorize a model within the brand. And my accuracy went up to 94.5%. So now about the app. Can we really do machine learning on the smartphone? Now it's possible thanks to iOS 11 and its machine learning core algorithm. And what can this app do? It can basically take a picture from the camera or your library, predict the sneakers, that's a history page, information page for every model, and an easy, fast way to find online sneakers on the website. So this is the app in action. So now I'm just going to see the model, the brand, and then going into the information for a specific model. Then I'm going to the story, and then I'm going to predict one of my favorite pair of shoes to track it myself. So just predicting it, that's it, easy, fast, and then just a button to click and buy a pair on the famous website, as eBay, for example. Yeah, so yeah, that's it, that's Sneakit, just an app I just made. And for future work, I'm going to add more branded sneakers, and I'm going also to do some photo shooting. I'm going to find nowadays by tune the data quotation parameters and implement new functionality.
Did I hear you correctly that you search for product SKU numbers in order to get your training set?
Basically, that was the only way for me to get a lot of sneaker images, as I wasn't really, didn't have time to photoshoot everything.
Did it make it harder to predict sneakers in real life? They're not necessarily on the
the thing is why I did the zoom basically on my app, because a lot of Google images are basically zoomed and really specific with a wide by one. So I had to do also a lot of manual filtering on my data.
Hi, Jeremy. Very nice project. I didn't understand how many labels did you have and how many training samples did you have per label?
So basically, I decided to go with approximately 12 models, 12 sneakers models, and every model was approximately 2,000 images divided into training, testing, and validation sets. So around 70, let's say 65% training, around 20% testing, and 50% validation set.
Okay. So you talked about accuracy. Did you look at the ROC curve as well? And did you see that maybe some class or some label was being predicted better than the other?
Yeah, the thing is, I also went for really balanced data set, and I basically went for 2,000 images for every model to have a balance set. And also the thing is, the accuracy is not really, it's like a good metric for my case because I have a balance set, and also I don't have one model worth more than another one. So, but the thing is, I didn't really look at the other recall and precision, because first my data was a bit poor, and I had some redundant information and images I couldn't filter by myself. So the way to really assess my data would be to take new data, read photoshoots, and know using the one I just used. This is just your prototype.
How did you make sure that your models didn't overfit?
I run a lot of models. On multiple AWS instance, and I tried from 10 epochs to 60. It took me some time, but worth it.
Hi, my name is Camila Nawaz, and my project is on predicting car crash severity for emergency vehicle response. The problem that motivated this project and that I engineered it for was a situation in which 911 operators receive calls about car crashes and must immediately ascertain whether or not there's an injury involved in order to decide how to prioritize and where to allocate EMS services. The source of the data for this project was the New Jersey State crash records for 2001 to 2016. I used data separated across over 950 tables. Ideally, the dispatcher will have to ask very few questions in order to determine the severity of the crash. So I pulled and decoded only the data that someone who had just been in or witnessed the crash could answer. Here you'll see a list of the features that were included in the final model. For instance, pedestrians and cyclists, ejection, and number of vehicles involved have highest feature importance and should therefore be immediately addressed by the operator. The target that I predicted was a classifier to determine the probability of injury involvement or property damage only. The final model was a random forest with an accuracy of 78.5%, and this was tested across the entire data set of about 4.5 million cases. This RSC curve shows the false positive versus the true positive rate. In this case, false negatives or type 2 errors mean that someone's been injured and no ambulance has been sent. So this situation requires that we find an appropriate balance between true positives and true negatives. In this case, we might want a threshold of about 90 to 95% probability that no injury has been involved before we decide to not send EMS services. And in this situation, false positives mean that resources were wasted. Moving forward, I'd like to improve the accuracy of the model to perform with more of a margin against the baseline, bring in more data from other states, and classify level of injury to determine the type of medical services to be sent. So again, my name is Camila Nawaz. Thank you for hearing about my capstone, and I'm now happy to take any questions.
So I have a question. You listed the features that go into the model. So would an actual use of this model be to have the dispatcher ask all of those, or were there certain ones that were maybe more important that could lead you to a quicker classification?
Yeah, so I think the ones that I've listed right here in bold, so pedestrians and cyclists involve ejection and number of vehicles have the highest feature importance in the random forest. And so that would indicate that those should be answered sort of immediately. And then the dispatcher can also take into account sort of time of day, atmospheric conditions, and posted speed without asking those to the person calling because they'll already know it. And I think that would help them determine the severity of the crash.
Thank you.
Maybe first you mentioned you did two models, injury involved and property damage. So were they two separate models, and how did they compare? What was different about it?
I'm sorry, so you're asking if it was two models for property damage and injuries? No, so it was like a binary classifier in the sense that I interpreted the 0 as property damage only, and I engineered it for property damage only as the 0, and the 1 would be that injury is involved. So it wasn't two different models separately. Yeah.
What was the class distribution like?
The class distribution was about 76%. And with the note that I do believe that people, there is a bit of underreporting in terms of property damage only crashes. I don't think that every time there's a vendor bender, someone's going to immediately call the police and it didn't show up. I think that in that case, like the minority class is a bit underreported. So I have to take that into account and knowing that that is definitely a flaw in the model.
Was the audio data also available? That could have been an interesting thing to study.
What was that?
The audio data, was that also available? That would be an interesting thing to study also, in addition to the text.
It's what was available?
Audio.
Oh, yes, that would be.
Like, how did you compare with the real world? I'm assuming they will send only AMR ambulances, versus, just police, when they think based on the leading question, right, there's a high probability. So did you have that data as well? Could you actually compare your model versus, the real world, when they will send AMR versus not sending AMR?
I didn't quite understand that.
Could you compare your model with the real world? So in other words, did you have the data on EMR? That crash?
If they went to the crash or not. Actually, I don't have that data, but I do believe that the ones that are listed here are the ones where there were police at the site. So if that answers your question.
If you had police and EMR, if you knew when they sent.
No, sorry. No, I don't think
because
so.
Because I'm assuming at the end of the day, what you want to do is save money, right? So you don't want to send EMR if there's no anybody involved, right?
Absolutely, yeah, that would be another really interesting thing to look at.
Hi everyone, my name is Nikhil, and my DSI Capstone project is called Movies Project. I wanted to create a different type of recommender system that kind of learned unique relationships between the items it was recommended. But one question I had was, is there a mathematical relationship between different movies? So if you took one movie and added to another, you get a third movie that kind of made sense. And the third thing I wanted to do was apply everything I learned in this program networks using a model that kind of combines both approaches called word-to-vec. So if any of you guys are not familiar with word-to-vec, some basic background on it is that it's a shallow neural network that basically predicts a word given its context in a sentence, given the context words. And the unique thing about this model is out of it come vector representations for the words themselves. So you can do cool mathematical operations on the words and see kind of analogous relationships. So I wanted to apply this to movies. So this is my processing pipeline. I started with data set of movie lens data that was about 45,000 movies with 48,000 unique tags. And after some processing, I got the data points to look like this. So for example, for the movie Godfather, I had a bunch of tags like crime, Al Pacino, oranges. And then I got my word-to-vec model and trained it on all these tags as sentences, basically. And out of that, I got tag vectors. So I got a vector for crime, I got a vector for Al Pacino. But ultimately, I wanted vector representations for the movies themselves. So I tried a couple different approaches, but I settled on averaging all the vectors for the tags for a particular movie, representative movie vectors for all the data in my data set. I created a web app that users could input movies and tags and basically add and subtract them. That operation, I checked the cosine similarity against all my movie vectors and basically returned a list of the top 10 closest movies. So this is my basic web app interface. I'm still developing it, but I want to jump to the results my recommender can do. So you can give it one movie like The Godfather, and it'll give you similar movies like Godfather Part 2, Scarface, Goodfellas, which kind of makes sense. They're all kind of movies. But what I was more interested in is that movies of like different genres, you can kind of see some sort of genre overlap. So if you had sci-fi plus romance, you get a list of movies that are kind of a blend between the two. And a cool thing you can do is, since the tag vectors and the movie vectors exist in the same vector space, you can add and subtract them from each other. The movie GoldenEye subtracted Pierce Brosnan, added Daniel Craig. The top 3 recommendations are so Skyfall, Casino Royale, Quantum of Solace. So I thought that was pretty neat. More examples. I do want to say there are some limitations to my model. Just gave it the tag of drama. I hope to see top drama movie recommendations, but what ended up happening was in my large data set, all these recommendations are basically movies that just have the tag drama and no other tag associated with them. And obviously that 100% cosine similarity to the tag drama. What I wanted, but it's an interesting thing to think about moving forward. Some next steps I have is to continue to develop my class web app application visualization to better add and subtract directors, screenwriters, actors and actresses, maybe scrape some additional data from IMDb and kind of standardize those features. Visualization of kind of T-SNE or k-means clustering to basically visualize these vectors I have in lower dimensions of how they group together. That's my presentation. Thank you for listening. Again, my name is Galvanize.
Awesome project. I can imagine someone spending hours looking at checking their favorite films and trying to see them. But I was a little bit disappointed that you didn't talk about Bigfoot sightings.
Oh, yeah.
Seems like that's a project that you worked on.
Yeah.
That's all I
We talked about again. You work back on every single one in the description. What did you end up maybe doing some filtering or figuring out or to weight those worlds to have reference on this?
Yeah. So sorry. So basically, I do kind of weighting different words. So one approach I'm thinking moving forward is to possibly TF-IDF on weighting them kind of the influence of more common words in my user tags and basically the influence of common words. But with my word spec model, I did set a parameter that had a minimum word count. So these tags are user tags that don't really make any sense. I mean, not a lot of them, so a few of them don't make some sense. So something will have a long tag like, do not watch this movie when you're feeling sleepy. And I basically treated that all as one word model. So if I set a parameter for a minimum word count, those tags that don't really make sense kind of fell by the wayside.
So you did one gram and n gram.
Yeah. So I treated phrases as basically multi-grams. I treated phrases as one word.
Did you thought about maybe also using topic modeling in addition to one back?
I thought about that as well. I thought about different recommendation approaches, collaborative filtering, topic modeling. I didn't want to go with the route where I was using user rating data because I know that's been done. I wanted to basically look at the metadata because I thought that describes the content of the movie better, and then the mathematical operations kind of make more sense when you see that. Thank you.
There are several diseases for which there is no accurate and early diagnosis even today. The disease may be detected when it has already advanced enough because of the presence of the major symptoms, and even then, the diagnosis may not be accurate enough. And my talk will emphasize how machine learning can be used for early detection of disease. Disease is one such disease for which we don't have early accurate diagnosis even today. It's a disease of the nervous system which causes tremors, stiffness, difficulty in movement, and it affects more than 10 million people worldwide. With the decreasing cost of genome sequencing data, we are seeing a rise in the genome data, and we have been able to sequence the entire human genome. RNA sequencing is a specific sequencing technique through which we can measure which genes are being expressed in a cell. So in case of Parkinson's disease, there is no cure. But if we can build a machine learning model based on a person's genetic makeup, then we can detect the disease early, and it can help alleviate some of the symptoms of the disease of the patients, thereby improving the life of the patients. But the genomics data is very high dimensional. Not only it is very high dimensional, it is highly variable. It comes from a variety. It comes in a variety of formats from a variety of sources. I worked on a RNA sequencing data set from 53 patients measured on gene expression levels of 60,000 genes. This is a perfect example of low sample size, high dimensional data set, which is very frequent in genomics, and it is because it is very difficult to obtain
patient information from the hospitals. So in order to filter the signal from the noise, it is really important to reduce the dimensions in the data to collect a subset of genes that are actually relevant to the disease, which calls for dimensionality reduction in the data. So if we predict the disease based on a time course, there will be approximately 50% accuracy on the prediction. I built a machine learning model using gradient boosting classifier on a subset of genes which were obtained using feature importances from random forest in conjunction with principal component analysis, and I obtained 75% cross-validated accuracy on my model. So why is machine learning important? So as I talked earlier, there are some diseases for which we don't have any accurate and early diagnosis. Parkinson's disease is one such disease. So if we can use machine learning model on the person's genetic data and predict the disease early, it can improve the life of the patients. And furthermore, the accuracy developed from just 53 patients was quite high. For future work, I'm currently using data from 53 patients, which is very small. So if I can incorporate data from more patients, it will lead to a more robust model. Also, there are a lot of genetics experiments have been performed which measure which genes are responsible for Parkinson's disease. So if I can incorporate this finding into my model, it will help in feature selection, and it will also make the model up to date with the modern biological discovery. My name is Himani Agrawal, and I built a gradient boosting classifier to detect Parkinson's disease. I will be happy to take questions.
Very interesting project, Himani. So I've got two questions for you. One, do you have a data set for non-humans, for example, mice, wherein the number of samples is larger than humans? And two, can you think of any disadvantages of using PCA over some other methods for dimensionality deduction?
The first question is if I can obtain data from mice other than the humans?
Some other animal other than humans.
So I think that would be really interesting because obtaining human data is so difficult. There is so much privacy issue. So in this case, if we can test some diseases which are common in more than one animal, and I think that data can really supplement these models since we don't have enough data from human beings. So I think that's a great idea, and we can really look into that once I have more data from mice or say other animals. But I'm not sure if RNA sequencing has been done on mice data. I'm not sure about that. Regarding the second question, so if I understand correctly, is PCA better?
Can you think of better ways to do dimensionality deduction than PCA?
So I actually implemented several methods for dimensionality reduction. One was feature importances from random forest. The other is k-means clustering, where I perform k-mean clustering to find groupings of genes in my data. So that is one more method of dimensionality reduction. Ultimately, I choose the method that has the best, that best increases my cross-validated accuracy in that model.
I have a question. What was the distribution of the response in GBM?
You mean the labels?
Yeah.
So it was quite balanced. It was 50%. So among 53 patients, I had almost 26 patients that were positive for Parkinson's, while others were not.
And so you did dimensionality reduction prior to plugging into the GBM. Why did you select to do that instead of using some of the built-in regularization methods of some of the advanced GBM toolkits?
Okay, so there are a lot of genes which are not relevant to the disease. So as I said, it's important to filter the signal from the noise. So it's really important to find only a subset of genes that are really relevant to the disease before doing any classification.
Thank you.
everyone. My name is Ino Edward Ra, and the project that I have the privilege to present to you today is natural language processing in Korean. To be more specific, unsupervised real-time topic extraction from Korean news articles. So my motive for choosing this project comes from my interest in learning NLP techniques for my native language and applying the knowledge I learned at Galvanize into the language as well. So the topic extraction goes like this. You first retrieve 1,000 articles based on a keyword and a time relevancy, which uses a custom function to search through the articles, and then uses a doc2vec model to instantly map the articles to a vector space, and then clusters using a density-based clustering algorithm. And all this is grounded on a local Elasticsearch database that is constantly updated and right now contains about a year worth of Korean news articles. So as an example, I ran a search term Samsung through my model. I was able to get 6 clusters, which is I didn't set the number of clusters, that was unsupervised and completely automatic. And there was a cluster about Galaxy Note 8, Samsung's new AI chatbot called Gritty, some news about baseball, which because Samsung has a baseball team in Korea, death of the previous chairman of Samsung, vice chairman's trial and jail sentence of Samsung, and other non-cluster news articles, which includes everything else. And here's an example visualization of cluster number 1, which is about the Galaxy Note 8. And the biggest word is the note. And this is the flowchart for my model. As you can see, it's divided into 3 major parts: data collection, indexing and searching, and clustering and visualization. The data collection includes the text processing part as well as the data collection. Indexing and searching also includes the model training part, and the clustering and visualization is the part that I just explained with the Samsung example. So the difficulties with cleaning Korean text comes from the existence of Omi and Chosa, which are kind of like the modifiers of the Korean language. And they mean word enders, or they attach themselves to the end of the base word, and you have to get rid of them, and that would, in order to make it machine learning friendly, and that would be considered the lemmatization for the Korean language. And the reason this is hard is because of the existence of combinatorial words, foreign and hybrid words, which uses like foreign words combined with Korean words, except they're together, and complicated exceptions and synonyms, homonyms, which are not always logical, which requires the use of a tool like con-NLPy, which is a speech tagger. And another difficulty is like, because the language, the words are pretty short in Korean, Samsung is only 2 characters. You can't give it a fuzzy parameter for only 2 characters, and because that would just get all the search results starting with Sam or ending with Sung. And you can't do prefix matching because of the combinatorial words, which creates a lot of noise. So right now, the score metric for the search is based on a text-based text match and the lemmatized text match, best out of those 2, multiplied by the date score with a Gaussian decay. And for future work, I'm going to improve the search function and make use of the untapped sentiment data which was included in the articles. People can choose, oh, I like this article, I'm angry, and whatnot. But largely that data has been untapped for now. And add an automatic and continuous doc2vec training system. Right now the model is fixed, and improve the text processing parameters. Thank you. My name is Inara, and I made a topic extractor for Korean news articles. If you have any questions,
That was a very interesting presentation. It's interesting to think about natural language processing in another language and the challenges associated with that. Did you also know the source of the article? Was that also helpful in disambiguating a little bit what the topic is?
Yeah. So the sources of the articles are from 10 Korean newspaper sources. I chose them because they're the general newspapers. They cover a wide range of topics. And right now I have around 800,000 articles, which is about 4 gigabytes of text data on my computer.
It's really great and unsupervised method for topic modeling. The question that I have is, how do you evaluate the quality of your topics? Do you have any metric wherein you yourself as a human being are not looking into how your clusters look like, but you have some metric that will tell you that your clustering worked very well.
Right now, I don't really have a non-human way of confirming the quality of the data, but I did take, because of the clustering method, which is a density-based method with noise, it will only take clusters that are almost 100% sure to be a cluster, and then things that are the outliers, which are the yellow points here, which doesn't seem to have isn't the data points that aren't part of a density group are clustered as a noise cluster. So I can potentially measure the performance of the model by counting the number of the articles in the noise cluster. So if there's more articles in the noise cluster, it might mean that the articles just have high variance, or it might mean that the clustering isn't as good as it could be.
Yeah, I actually have this question along the same lines. How like coherent the way cluster and analysis actually articles within the clusters? How coherent are actually articles?
Right now, it's hard. I don't really have a specific average because the model requires me to manually search for a keyword. But in general, I've noticed that the noise cluster, the size of the noise cluster out of 1,000 articles is around 300 to 500 articles, and whereas the number of clusters are anywhere from like 3 clusters to like 7 clusters. I can't really put a specific number on how that. I can't really interpret that in terms of a solid statistical performance-wise. But I know that there are improvements that I could make to the model right now.
Great, thank you.
Hi, my name is Anusha, and my project was to build a recommendation system for Udemy users. So whenever I try to enroll in a course in Udemy, I always check out the ratings of the course, see how many people have enrolled in that course, and watch some preview videos to get a feel for the course content. So I basically spent a lot of time before I decided to register for the course. So I decided to develop a personalized recommender system and a web app to recommend courses for Udemy users. And this is the homepage of the web app I developed. So I got the data from Udemy API, and as you can see, the rating scale in my data ranges from 0.5 to 5, and my utility matrix is very sparse, and more than 75% of the users have rated courses, have rated 2 or less than 2 courses. So I treated them as cold start users since I will not be able to evaluate the ratings from these users. So for the cold start users, I use the quantitative model to recommend courses. The top 20 courses. So if a user picks a course from this list, my web app also displays the courses that are similar to the course that the user picked. So in the upper right corner, the courses displayed are similar to Reiki course, and in the lower right corner, the courses displayed are similar to Learn Digital Marketing course. And the similarity between these courses are measured using Pearson correlation. And for the regular users, I used matrix factorization to recommend courses. So I manually split the training, validation, and test to represent all the users in the training data. I also performed two-fold cross-validation to avoid overfitting and to find the optimal parameters to use in my model. And the evaluation metric I used was root mean squared error. In my final model, I used LDA to extract latent features from text reviews as well as from the course topics. The reason why I took 2 latent features from text reviews is because I read through some of the reviews, and when the user gives a review, it was about a video quality, instructor's knowledge on the course, and one was also about the course content. So I went with my intuition to go with 2 latent features for text reviews. And for the course topics, I tried from 4 to 20 number of topics, and with 60, I find that the topics were more distinguishable and interpretable. And with the test RMSE, we can see that matrix factorization with side data added gave a better results than the other models. And for this particular user, based on the courses that he has already taken, these are the courses that my model recommends. Future work, I'm planning to include instructor bio in the model to address the gold star problem for courses. And I also wanted to account for the user bias and item bias in my model. And I wanted to add more features to the data. Thank you.
Did you only have access to the user ratings data? Do you also have some information about the courses that have taken, completed, or returned, and such? What would be?
So I just have the user item and the rating, and some item data, the price of the course as well.
How do you think you would have taken advantage of such data if you knew whether or not the other individuals weren't able to
maybe the implicit feedback? Because at Udemy, I think they must have actually have the implicit feedback as well as explicit feedback. I'm actually using the explicit feedback one with the text reviews because I wanted to do some sentiment analysis on the text reviews as well. But with the search history and the implicit feedback, I'm sure that I'm more than that.
Thank you.
So what do you think was the most challenging thing in the project, or what kind of data maybe were you missing that you would like to have?
Maybe some more like item data and user data because I didn't have access to the career or the interest of the user and the age, and also the main reason why I wanted to do this project was I wanted to give a personalized recommendation for the user, accounting for what the user is currently pursuing. So with the collaborating filtering and the neighborhood mode, I was able to achieve that with more data, like user data. I think the model would be more better. So I had to extract features from the text reviews as well as from the course topics to get more data to add as user data as well as the item data.
Hi, my name is Praveen, and I'm here to talk about graphic sign detection and classification. Around 1.25 million people die every year due to traffic accidents. Autonomous cars could be a potential solution, but one of the biggest challenges they face is to identify and detect traffic signs. In previous researches, people tried to focus just on the traffic sign and try to classify them. But cars actually see a lot more of noise and less of the traffic sign. My project scope was to try to classify these kind of images using CNN. The data source I obtained was from UCSD, and although they had multiple traffic signs, I just used the top 3 because that contributed to 50% of the data they had. And they also provided the information about the bounding box, which is the pixel location of the traffic sign in that image. The first process I did was using transfer learning using VGG, and it gave me an accuracy of around 17%. At which point I kind of thought maybe accuracy could not be the right metric, especially for a multi-class classification problem, the right way to go. And that was my first roadblock. I thought about using precision and recall, but then they were not implemented in Keras. And that's when thinking more about it, I kind of realized that my categorical cross entropy has more information about how the model is learning. And I thought I should use that as a metric rather than anything else. The second roadblock going into it was the data size, because there was only around 3,000 odd images, and my model was not able to learn well from that. As you know, deep learning models tend to perform better with more data. And I thought about collecting more data, but given the short time frame, I did not think it was a feasible option. So I turned to augmentation as one of the processes to increase the data size, like flipping, rotating, and translating images. But as you can see, flipping a stop sign does not make sense because PODS is not the same as stop. And the other problem is if you rotate an image too much, like 45 degrees, it's kind of like your car is at a 45-degree angle, at which point you have much bigger problems. So what I did was I just rotated to less than 10 degrees to kind of account for the backing on the roads. And I also translate my images, and it's kind of shown here. And at this point, I kind of wanted to build my own architecture and see if that was able to classify these kind of images better because the BGG was more generalized. And I realized that my image data had a lot of noise in it, and hence my model did not perform that well. At which point I kind of got thinking, what if I tried to push my model to focus more on the traffic sign rather than the noise? And that's when I kind of came into the fast RCNN paper, which kind of has two output heads, and while backpropagating, the convolutional layer weights kind of get more information from both the losses together. And this drastically improved my model, the loss coming down from 10R to around 1.089. And this is the final model which I used for my test data set, and it had pretty decent values, which is kind of what I expected it to be. But one thing which was kind of surprising was the pedestrian crossing, because even though it had a sizable amount of data, the accuracy, the precision in the recall was pretty not high. That's when I went through my data set to find that the shape and the color was kind of weird, that it matched with the background a lot, and hence my model was not able to detect that. So that, and yeah, just to make sure my model works, I kind of got images from Google Street View data, and it performed pretty well. So thank you, and if you have any questions, I'll be happy to answer.
Thanks. Great project. Until you passed RCNN, I was thinking, why did you first collect the bounding box and then train on it? So I'm glad you did it. That was going to be my first question. So the second question that I have is, how did your model perform when you had traffic signs in and out of focus and of different, when you had images of different resolution? Like, what was your input layer like?
Okay, I guess the resolution, yeah, so what I did was I did some pre-processing where I converted the image size to 350 by, or 450 by 450. So the resolution was pretty much the same. And yeah, so I did not run into that particular issue since all my images going into the model were of the same size.
But you didn't have any issues with the traffic sign being, you know, at a longer distance?
Oh, yeah. I kind of kept that as a future work because at this point from, you know, when I got the data source, it was kind of a mix. And I had to, if I had to implement that, I had to do it manually. And again, I did not have the time to do that. So I thought maybe I should do it as a future work. But yeah, definitely that would happen.
I have a question on bounding boxes. Were they similarly tight on all the images? And were there any images with multiple signs? And did they have multiple bounding boxes or anything like that?
There were images with multiple signs, as you can see here. There's one over here and one over here. But the data set which I obtained had just information for one of them. And it was clearly defined. So I did not think too much, but I'm sure my model would have been confused a bit. But I think it still would have performed better. Yeah, but definitely I should, the next, again, future work would probably have a multi-label, multi-class classification. And that's something going ahead. I hope I answered your question.
Yeah, perfect.
All right, folks, that took me surprisingly a lot longer to walk the long way around. Sorry about that. Okay, we're going to take a quick 15-minute intermission. So if you want to get up, stretch your legs, maybe talk to a couple of people, and we will see you back in 15.
Awesome.
You are all doing amazing. Thank you. These are great questions. Yeah, exactly. Here we go. Oh, yes.
Perhaps, yeah. I'm like really just looking to learn and see. I haven't even Yeah. It's done already. Like, are you
I have my master's from Boston University in economics. So because I'm kind of in between the same people to
yeah, me too. I mean, just to see resources in the solar industry myself, so I cool to see like, like the first project was so definitely. I was expecting to see the data be like business
No worries. I appreciate that. Contact your hiring and your flexible meeting.
All right. I'm gonna let our booming dulcet tones carry across the room, and I'm gonna encourage all of you to return to your seats, and we'll go ahead and get started. Are you ready? Cool. I'm gonna wait for everyone to sit down. All right, welcome back, everybody. There's plenty of seats. I see empty spaces, and I see people kind of filling in. All right, honey, I'm gonna go ahead and let you take it away.
Hi everyone, my name is Kenny. My project was focused on predicting eviction notices in San Francisco. So why predict eviction notices? Well, San Francisco is definitely not getting cheaper to rent in. Eviction notices are definitely not going down. In fact, there's been major spikes in eviction notices in the last 5 years. And being able to predict ahead of time that evictions are happening is something that both tenants' rights groups, city officials, as well as the average individual would be interested to know about. So the initial baseline. I picked a 3-month rolling mean initially by zip. This is one of those zips, 94134. And 2 things immediately stood out. Sorry, the blue here is evictions, orange is prediction. That'll be true throughout the presentation. 2 things stood out. One is the extreme amount of variance from month to month, which time series have a very hard time picking up on. And secondly, the outliers typically get propagated through for multiple time periods afterwards and any time-lagged prediction, and that can cause issues with prediction. So, predicting at a zip level seems not a great way to approach this. So I went back to the macro level and fitted a Serena model, so a seasonal time series model, and this actually did fairly well. So thinking about this, most of my work after this was focused on how I could harness this power, this predictability at the macro level and get it back down to the micro to predict on the zip level, which is the actual beneficial level in terms of this project. So initially I thought, were there features I could add to potentially improve the predictability? I looked at a number of features, 2 really stood out, and these were ones that sort of I hypothesized and also seemed to prove out. One was unemployment rate. There seemed to be spikes in unemployment rate that then were followed by spikes in eviction 1 to 3 years afterwards. As well, capital improvement requests. So these are made by landlords well ahead of when they actually do large capital improvement projects. And those projects typically result in evictions for those tenants. They sometimes get returned to their original homes, but it depends on the project. So modeling. I now have features, and I know I want to predict down at the zip level. So a random forest seemed like a logical first step. And so I used the zips, I dummified them as features. And this is how the random forest did versus the baseline. So negatives here is improvement, right? This is root mean squared error. So for 2 zips, it did very, very well. For a couple others, it did slightly better, and then it actually did worse for a number. So this was concerning. I didn't have a model that could predict better than the baseline across the board. But I looked at the features. This was promising. Top feature here, people live in San Francisco know that the mission has experienced regular and high eviction rates for the last 10 years. So seeing that as a feature of high importance made sense. And then the unemployment lag variables as well as capital improvement projects as well. I wanted to get back to being able to use this time series macro level to be able to predict on the micro. So I tried every sort of combination of features possible. I ended up using unemployment year prior as the exogenous variable. I did a top-down, and I ended up doing a top-down decomposition. So I essentially took the proportion that each zip represented of total evictions in previous time periods, and then predicted the next period of time for that zip based on the proportion beforehand. This is how it did relative to the random forest, so better across the board, save for in those 2 zips where the random forest had performed so well. So I decided to ensemble the 2 because they each seem to have some performance abilities that were different from each other. So I took the best of the random forest, the best of RMAX, ran through linear regression, and we ended up with this model. So I call this sort of like a variable trend line. It's capturing some of the variance over time. It's not responding too much to any deviation one way or the other, but certainly not just predicting a straight trend line either. Normally, this is where any sort of talk about time series would end, except I actually had test data because the city released data as I was going through this project. This is how I did versus the baseline of both of those. So I did better in the baseline of both the aggregate level as well as on the zip level. My name is Kenny Durrell. This is my project. I'm predicting evictions in San Francisco.
I have 2 questions. Number 1, what was the rationale behind trying to predict evictions?
Sure.
Yeah, and number 2, if you could get any data to improve the model, what would you want to have?
Yeah, so the rationale, going back to sort of that tenants' rights group, knowing ahead of time there's going to be a big eviction event, so specifically those outliers, is something that tenants' rights groups can potentially prepare for, as well as city planners. So having an influx of eviction notices, knowing that that's coming through, it's a court issue, it goes to an appeals board potentially, it's a complicated process to get someone evicted. So having that preparation, I think, makes a lot of sense. If I were to have any features, I think there are 2 that really I would love to have. One is the size of the capital improvement, so it doesn't tell you how big it's going to be. And a lot of those big spikes that you saw there are large capital improvements for projects. One was at Trinity Plaza, which is right around the corner. One was down in Lakeshore, sort of like southwest corner of the city. So knowing the size, I think, would be a really easy way to say, like, oh, in 2 years, there's going to be a huge amount of evictions in this area, sort of like the financial amount, I think. And then one other thing that I would have liked to get to is doing some sort of like similarity comparison between zips or between neighborhoods, doing some sort of like clustering to try to say, like, oh, these areas seem to like all move together, or there's some sort of pattern or way of going through the city. So doing maybe more feature engineering.
It's interesting to see that capital improvement project that was available. That's very clever of you to try that in your model. I wonder if demand-related features could also be interesting to try out.
Yeah, so I tried, so the only sort of demand-related features I tried average median housing price in previous months and years, as well as rental price over time. I guess other demand would be sort of like, I guess maybe like number of bids put in on certain places.
The inventory, the number of units that are available.
Oh, the number of total units. Yeah, I guess that too. Yeah. As that San Francisco was interesting, like, what? Yeah, I mean, that's part of the issue, right? Like the inventory is not high, or people are holding it out to try to get higher prices. So in terms of like predicting that, I think there's definitely something there, but yeah, knowing sort of like getting down to the building level or even like the permit level or like how many units are in the building is not a simple process. And with the 2 weeks, I sort of decided to focus on this. But yes, definitely those kinds of things that make a lot of sense.
Yeah. Did you have a question?
Yeah. Sure. Yeah. So I take the predictions from the random forest regressor, the predictions from that top-down decompose, and then put them into linear regression, essentially using those as variables that then feed at the end, and then that predicts. So it's doing sort of like a weighted average, essentially. Thank you.
Hi, my name is Jake Hawksworth, and I build a sparse matrix factorizer for Python. I took this project on because over the course of this program, we've had the opportunity to use these really amazing open source tools, and I wanted to try to spend these 2.5 weeks making some kind of contribution to that. On Recommender Day at Galvanize, we used GraphLab, which is a tool that's both proprietary and now no longer available for commercial use. So this seemed like a place to be right for some open source development. I knew I wasn't going to be able to recreate everything that GraphLab did, so I decided to focus specifically on the tool we used, which was the matrix factorization recommender and its predict functionality. So given user A's rating history, what's their predicted rating for item B? Now there are certainly tools in Python that are open source that are able to handle that question, but speed is a pretty big factor, and with recommender data sets, typically you only have somewhere between 2 and 6% of the possible user item pairs that include ratings, and to generate predictions for the other 96 to 98% of your possible user item pairs is computationally expensive, and even with medium-sized document collections, it could be prohibitively expensive. So I implemented in Python this algorithm written by Trevor Hastie, who's a famous statistician a couple years ago, called soft impute. And he gets around this issue using a sparse plus low rank matrix class that he came up with, which I also implemented in Python, that includes the user indexes, the item indexes, and the ratings for known user item rating pairs sets. And then the singular value decomposition, which you would use to generate the predictions for the missing values. So to benchmark my algorithm, I compared it to GraphLab. I wanted to see how close I'd be able to get to GraphLab's implementation, and also to existing options in Python that did destroy the sparsity of the data set by avoiding all the user interface. So using the movie lens data set, subset of it, I was able to get a 1.4 root mean squared error. This is in units of 0.5 to 5 movie ratings. Whereas GraphLab was at 1.2, so within 0.2 cross-validated root mean squared error. And from my model, and from a speed perspective, you can see this blue curve here is existing options in Python that destroy the sparsity of the dataset that are open source. Down here is my model, soft impute, which is not quite as fast as GraphLab, which I think is largely due to the distributed implementation that GraphLab has going on. So this package would be appropriate for pretty much anyone who has a sparse data set that's small enough to load into RAM that they want to use a matrix factorization recommender for. My soft compute package, it'll soon be available via pip. It's been unit tested, benchmarked, and licensed for open source use. And I'd like to make a distributed implementation down the road. Trevor Hastie's paper did mention that that was something that that this algorithm lends itself quite well to in his paper. And also to add more functionality to make it more comparable to what GraphLab currently offers. So again, my name is Jake Hawksworth. It is Sparse Matrix Factorizer for Python. Glad to take any questions. Thank you.
First of all, thank you for making a contribution to an open source project. That's awesome. I don't know if you shared, and I may have missed this, but did you also compare the accuracy of your approach to fancy impute, which is already available in Python? Or it sounds as if you compared it runtime?
Yes, sorry. So fancy impute is a very, very basic implementation of Trevor Hastie's model that destroys the sparsity. So actually, from a root mean squared error perspective, it's identical in terms of how it performs.
But faster, that's valuable.
Much faster.
Great presentation. Are there any other open source projects that are looking to potentially use this? Yes.
Yeah, you know, I did not have time to do a ton of research around what else is available. I know that implicit data, there's a pretty good set of options out there for recommenders, open source recommender stuff with implicit data. I did not find anything out there that did what this does. So. Does that answer your question? I might have misunderstood.
Oh yeah, that's fine.
I'm curious, is there a reason why there's results between GraphLab and the solution?
In terms of root mean squared error, those scoring unique, yeah. So I believe it's really hard to say because GraphLab is like the premier solution, and it doesn't actually, they don't give you access to the algorithms that they have going on under the hood. So it's hard to know exactly what's going on there. Yes, it is a slightly different algorithm for sure, the matrix factorization algorithm, but that's a whole sort of family of recommenders.
So, hi everyone, my name is Elham Keshavarzian. Thank you for your time. And for this project, I work on breast cancer classifier. So, to give you an idea of how important it is, we can see that in female patients, breast cancer has the #1 incidence, and also it has highest rate in the mortality. Also, if you look at the both genders, it is the second highest one, so it's not really far from important. And to give you a more personal reason that why I choose this project, Mariam Rizahani is one of the prestigious mathematicians who unfortunately passed away at the age of 40 because of the breast cancer around a month ago. And that's really pushed me that I want to work on this project. For the data, I use available online data from the Breakfast, and I was working with around 8,000 images, which was able as benign and malignant, cancer and non-cancer tumors. And they were taken in different magnifying levels, from 40x to 400x. To start with, I tried to replicate the model that was presented in a paper and try to see how far I can reach the results. Unfortunately, in that paper and also other papers that I read, the only metric that they provide was accuracy. But I wanted to also understand how well my model works, so I include other metrics such as precision, recall, and F1. So my model consists of 7 CNN layers and 2 fully connected layers, and my accuracy was very similar to what paper proposed. Then the next step was trying to improve on it. I tried a couple of things, but 2 things that really helped me to improve was image augmentation and dropout. When I was thinking about why it really helps was that for the type of project that I was working, it really doesn't matter in which angle you look at the tumor. And adding more dropout to each layer of my network helps to understand all of the signal, not just the highest and most important signal. In other words, it understands about the pattern of the tumor, not just objects. After running that, these are my improved results for my improved model. As you see, the accuracy really doesn't that much change, but other metrics improve. So the next step for me was that to see if I add basically more noise to my data, how much or how worse my model is going to perform. In my project, noise means breast tissue which is not tumor. So in other words, the 40x one is really focused on the problem area, whereas the 400x one has other tissue data that is not a tumor, so it has more noise for me. And as I was expecting, by increasing the noise, my result is going to decreasing. So I really want to continue with this project, and my next step is to be able to classify different type of cancer tumors. These are the type of images that I'm going to work with, and I have a basic model right now that this is the result for that. I will be happy to accept your question.
Very nice project. My question for you is, did you look at the training time and did you do any hyperparameter optimization?
Yeah, I did a couple of them, but I applied so many things to see how it performed. So many of them, they really didn't change a lot in my result. The main 2 important things that really change is the dropout, that I increase it in each of the layers compared to what paper proposed, and also having more data augmentation. Also, the other thing that I need to look at that I didn't go through that route is that using existing weight to apply to my model and start from that I didn't have time to work with that.
And did you train on the GPU or?
Yes, yeah. I was running a 2P2 GPU from AWS, and it takes about a little bit more than 1 hour for each round of training.
So in that paper, was that comparing against a different neural network, or was that against subject matter expert opinion?
So the images that was taken was from an expert taking that images and classified them as malignant or benign, but they compare it with themselves.
Okay.
Yeah.
Cool, just curious. Yeah.
This is in this is the paper.
And this is from the data that I get.
Wonderful. So would you anticipate a use case for this algorithm being to maybe pre-process images and provide recommendations following an expert opinion? Or?
Yes, definitely. Because right, like that's like a personal thing that I hear. Like a friend of me got diagnosed like a week ago, and it took about 4 days till they let her know if it is cancer or not cancer. Which I think that 4 days is really hard for anyone who go through that. If you can have something that an expert can, predict it much faster, I think it's really help. And also we can use that expert knowledge in really curing the problem instead of just, recognizing the problem.
Thank you.
Hi, my name is Matthew Wong, and my project was a PDF classifier for mortgage company. So for my motivation, this company gets hundreds of PDFs a day, and these PDFs are often sorted by employees, and this takes a lot of time. It essentially costs the business a lot of money because these employees aren't able to do other tasks. So my goal is to create a model that could possibly classify some of these PDFs so that employees could work on other things. So for my data, I had about 14 different imbalance classes, ranging from like appraisal documents, escrow documents, insurance documents, and such. There's about 700 PDFs, and the PDFs in each of these classifications varied in both length as well as type. The length would be either from like one-page invoices saying, oh, this document was sent or received on this day, to 30 to 100-page reports. And these came in forms, scans, faxes, and even sometimes pictures of like income statements. So for the first step was text extraction. I used 2 different modules, PDF Miner as well as PyOCR, which was a Python wrapper for tester app. And the differences in these two were that the PDF Miner worked well for the forms, but wasn't able to extract text from scans. So that's where the PyOCR came in. The also difference was that the OCR took a lot longer. So I used 3 different models. I used a naive Bayes model and 2 TF-IDF cosine learning models. The first cosine learning model I used was averages. I took the average of cosine similarity between all the documents in a category, and this was to try and capture the signal from the variation in all the documents. And then I used the KNN type cosine similarity model where I just looked at the top and most of the documents. Also used 3 different sets where I just used PDF Miner, which left all the scans and anything that wasn't basically a form blank. I used the PDF Miner and PyOCR, which took all those blank documents and then used the OCR to extract the text from those documents, or just the OCR model. And as you can see, the PDF Miner and OCR combination actually performed the best. And I believe that happened because the OCR actually took a lot of the noise around the specific or other documents that I wasn't able to get text from, just the accuracy. So depending on the threshold that employees would want, they can look at specific classes and say, the 5 classes that say were under 80% would always be hand checked by employees, and the others could just be classified as that. So for future work, possibly renaming and following documents automatically to again save employees' time as well as extracting specific text strings like a name, address, and all of those. So again, thank you. My name is Matthew Wong, and my project is a PDF classifier.
Should probably let you ask. You have no idea how many companies actually deal with such challenges, data coming in PDF files or scans, etc. I wonder if there were any special structures in at least some of the classes that you could also explore in addition to type of words, type of approach. Have you noticed anything that you should work better for some classes?
So for the classes that actually had a lot of different documents, these actually worked very well for. But when I was looking at some of the classes, like 2 of the classes only had, I think, 4 or 5 documents inside, and they were basically just like, oh, this is photography or something.
That's the size of the class.
Yeah, so it was more just
basically getting more data on the different types of documents in those minority classes would help improve accuracy.
Great presentation. This is great, and an active area of research in many industries, including my own. So I'm just curious, the ones that were classified with low probability that you said would have to be manually checked still, were those very similar types of documents, or were they still quite different?
So the word usage in those documents were very similar, so it sometimes had a hard time distinguishing between the two, but I also implemented where it also had a threshold, so if the cosine similarities were too close, or if it only voted, say, like 3 to 4, it would also display, oh, you know, these documents should be checked by hand because they're very similar. But if we were just looking through, say, the cosine similarity and which documents were available, it usually predicted pretty well.
Great. And you mentioned some accuracy statistics. Was that on testing sets, or what was the framework for those accuracy?
So these accuracy numbers, these were on the test set. I used also a stratified cross-validated score, and the only differences were that the test set didn't have the same number of imbalance classes, so that's why the accuracy was a little bit different. So that's why I put 5 and 7, because it changed between the test set, the cross-validated.
Thank you.
One more question. It's a tough question. You know, given that we have heard it's a common problem in the industry, I'm going to give you a hypothetical situation. So you have PDF scans of newspapers, okay? And you know, the layout of every article changes every day. So there's a big headline, and then there's one article about politics, another one is an advertisement. How would you go about classifying these articles from PDF scans of newspapers using some of the techniques that you have presented?
That's a good question. I'm not exactly sure, because each of the PDFs that I got were specifically labeled, so I'm not exactly sure how I would go about classifying these articles, but possibly looking at a specific portion of the document, and then possibly getting labels from those, and then training a model on that would possibly be one of the first steps I would take. But yeah, that's a problem that I didn't really do too much time today.
Thank you.
All right. Hello, everyone. Thank you for being here. I am Joseph Fan. Today, I'll present to you T-Watch, a product I built that can process streaming data with the help of Kafka and Spark Streaming, and make real-time sentiment predictions with great scalability. So my motivation is to build a data product that can do machine learning at scale. It can process streaming data. It has a end-to-end data pipeline. It can generate automatic reports. It has scheduled model updates and test monitoring. So here are the few tools I use to make this product possible. So for the current version of the product, it has a web app that can do sentiment prediction of the incoming Twitter streams. It can perform search graphs. It can send out message alerts with user customer conditions. It can generate basic data email reports. It can do weekly model training and updates. And then all scripts run on EMR on AWS and can be scheduled and monitored by Airflow. So this is a quick look at the real-time data flow. As you can see, Spark Streaming is like the core engine where most of the magic happens. So let's take a deep look. So right now the input source is Kafka, and the Spark Streaming basically do real-time sentiment predictions using the pre-trained model, machine learning model, and it goes out to 3 different sources: message alert through Twilio, storing MongoDB to be published later in web app, and storing S3 for longer time storage. So for the model training part, I trained a pipeline that trained together hashing term frequency, inverse document frequency, and random forest classifier in Spark MLlib. It is over a data set of 1.5 gigabytes of over 1 million tweets. And I also compare with other classification model like XGBoost and recurrent neural net, but I choose this for the sake of less training time for my project purpose. So this is the homepage of the web app right now. You can see all published tweets. You can check topics, some basic charts, and you can do search on those tweets. And this is a publish of the tweets. This is a showing of all the positive tweets where the prediction is 1. And here are other features like search, graph, and the message alert. And this is right now it's only a basic version of a data email report. It's sent out via Amazon SES, and it contains a basic table and a graph. And for the future, I want to integrate deep learning for training language model, and I want to improve feature extraction for very messy social media feeds, and also maybe use a more robust and scalable database like Cassandra. Thank you very much. I'm Joseph Fan. I'm happy to answer any questions.
You mentioned having implemented some scheduled model updates. Tell us a little more about that.
So basically, I write some Airflow scripts that train together either a Python operator or bash operator. Those like Python script take command line arguments for like user defined like conditions, and every day you can start and stop EC2 instance, and also schedule the time of streaming and schedule the time of like because right now I have like 3 Kafka that output different type of topics, and you can close and start different type of topics you want to track, like based on your purpose.
If there was some sort of a feedback that would let you know what the model performance is, and can you think of a way to expand on this particular architecture so that you'll be able to see whether or not your model is performing well and message someone when it's not?
Yeah. So I'm really a big fan of like agile data, like product development purpose. Right now, the random forest model is not that great because like the feature extraction in the text in tweets is very messy. Like people spell all things like incorrectly all the times. But in my like service, in my product, like all sections like are encapsulated individually, so that you can train a model that without changing other parts. Because I'm saving the model in a pipeline, so once if you want to train another model that has a better accuracy, you can just change the part of the training model.
So what did you use to handle the environment for all this software, like Docker?
I basically just write my own bash script to launch the EMR, and I installed all the packages I want. And so like if I want to like if my like EMR fail or something, I can just launch another one at any time I want.
Thank you.
Hello everyone, my name is Jay, and my capstone project is the movie poster genre classification. So as we all know, the neural network is widely used in the image recognition problem, and they are actually very good at capturing the shapes and outlines of the specific objects. So my question is, how well could the neural network capture the abstract meaning from images, like the genre from the movie posters? So I scraped my data from IMDb
database. I got over 37,000 posters with 28 genres, and many of the movies has more than one genres. Project narrowed down my scope. I have 9 major genres, each often has more than 3,000 movies. But they also have some overlap between the similar genres. For example, the action and the adventure actually share a large amount of the movies. And eventually, I end up with 4 most common genres with the least overlaps. So they're adventure, documentary, horror, and romance movie. So on the right side is the genre co-occurrence heat map. The lighter the color, the fewer the overlaps. So my final model is a 7-layer convolutional neural network with 5 convolutional new layers with 2 fully connected layers. And the final validation accuracy and recall precision is around 70%. So I also developed a web app for the user upload images. So this is a prediction page for my web app. So for Inception, it's 100% adventure in this case. So there are some of the posters my model is actually doing pretty good. Like the Skyfall is mostly adventure plus a little bit romance. The Jurassic Park is mostly adventure, a little bit romance, and a little bit horror. And for the Man on Wires, definitely 100% documentary. The Garage is actually horror movie here. There's also some of the posters my model could do better, like the Martian and the Hidden Figure are categorized as the romance movie. It's mainly because they have the close look on a human face, which is highly correlated to the other romance movie. And La La Land and La Mise are categorized as a documentary movie. Because in many of the documentary movies, they have the wide landscape of the cities with the tiny people in the middle of the posters. So that's my intuition. So we can also use the user customized images. In my web app, I can upload the images, whatever image you want. So as we can see, with the single human face and close look on that is mostly romance and a little bit horror. And with 2 people in the middle of the poster, it's definitely 100% romance. And with the darkness in the background and the shadow of the people, it's mostly horror, a little bit adventure. So for my future work, I will try to do the multi-layering on the movie poster and try to predict more than 1 genres for each poster. And I will try to group the similar genres together to strengthen the signal in my model. And I will try to extract the test information from the posters. Because sometimes the movie may convey more information than the poster itself. And thank you very much. My name is Jejo, and I'm happy to take any questions.
A great presentation. What was your data set like? How many images, posters did you have per class?
Yeah, so initially I have 9 major genres with more than 37,000 posters. So after I narrowed down to 4 genres only, like the horror, adventure, documentary, and romance, is around 15,000 posters.
And did you actually look at the weights of the layers to see what they were learning, like the first layer, second layer? Did you try to understand?
Yeah, actually I try to visualize these intermediate layers. So they're kind of capturing different shape and colors. We have 3 channels, the RGB channels. So usually like the horror movie, they like more like to capture the dark background and the kind of the creepy smile, those kind of thing. Yeah.
All right, thank you.
Thank you. I was just curious, what did you come up with the idea? And then what did you learn from it? And how do you think you could end up using that?
Yeah, so my initial motivation is because we all know like the neural network could be very precisely predict the specific objects, like the fingers at hot down, and like they can actually they're very good at capturing these shapes and outlines of the objects. But my intuition is like how well could they kind of capture the abstract meaning from the images, like the sentiment analysis on the images, like whether they can predict the people in the images are happy or are they sad. So kind of do this emotion analysis on the images. So one of the application of this general classification I can think of is the production team of the movies. They could kind of see what kind of marketing strategy they want to use. So as I mentioned before, so like La La Land means they are actually more like a romance movie than a documentary movie. Maybe the designer of the poster, they don't want like the stereotype romance movie poster, and they want to apply a different approach and use different designs. So they give them a guideline and see what's the trending pattern of the current current poster in the particular genre they are marketing, and they can use that as a reference.
Thank you.
Hello everyone, I'm Shige Tajima. I will present my Capstone mortgage data analysis. This project is for mortgage lender. So here the brief summary of loan processing stages. When the customer contacts the company, a lead gets generated, and after that the rate becomes locked, and eventually money gets funded. And my project is to predict the lock to funded, which is number of days from the rate locked until the money gets funded. And this is the most important keyword in this presentation. Here are the motivations. So the company ideally wants to predict the lock to funded time, which means that here when the rate becomes locked, they want to know how long it takes until the money gets funded. And it costs time for the company so that they want to reduce the lock to funded time. They also want to understand and identify most important features. And those things will be beneficial to both the company and customers. The data set, so data is from a mortgage company in the Bay Area. And there are many features like 500, including 200 categorical features. And those are like field costs and status and information about customers and companies. And one unique thing about this data is that the loan processing procedures changed a few times since the company started, which affected the lock to funded time. So here is a plot of lock to funded plotted against the number of months since the company started. So one way to model this is just to use regression. The other way is to use the lock period. That's a discrete numbers. This was obtained by dividing data into several different bins and then do the classification. So I also added a new feature by analyzing data set. From the number of active loans per day, I calculated the average number of active loans for each loan case. And this was further normalized by the number of available staff for each day to get the loan rate factor, which shows the correlation with the lock to funded. In fact, this is I found one of the most important features. So here is the regression result to predict the lock to funded. So I found the two dominant features, which are key for extending the lock period and the loan rate. And I used several different models, and the best one was the gradient descent boosting validation R-squared score of 0.66. And also I used the classification to prediction of the lock to funded period. So the data was divided into 5 different bins and used random forest to classify them. And I used the top 50 features out of like 600 and do research to optimize parameters. And I got the random forest cross-validation accuracy of 0.54. And shown here are 4 dominant features which are related to those things, which are actually the thing as what we found called the regression models. The future work, those types of pair performance analysis can be done to identify, for example, good pair performance. And also we can predict other things like a lock to clear to close. This is a major milestone before money gets funded. Thank you so much, and I'm happy to take your questions.
What was your customer's intuition about the variability in the lock-to-funded time? So is it mostly caused by the company itself, or something that their clients need to perform?
So company is more interested in this lock-to-funded time because it costs money if the time becomes longer. So there's a so-called lock period. So when the money gets funded, when the rate becomes locked, the company assigns a lock period such as 30 days, 45 days, or 60 days. So if it's ideal if the company can predict the correct lock period.
To follow up on that question, in that lock-to-funded period, information that the customer has to provide, or is it just essentially processing that the company has to do?
So there are a lot of things which are involved, and then because this data set I use has a lot of customer information as well as companies information, including staffing availability and also staffing staff performance as well. So there are a lot of things involved.
Regarding the classification application here, did you do any analysis on the misclassifications to see if they were maybe, just one level off or maybe 2 levels, if it's from the first level to the 4th level, for example?
I didn't have a chance to look at it, but that's a great comment. I would like to take a look at it.
No problem. Thank you.
Thank you.
Hi everyone, my name is Kelly, and my project is to provide personalized perfume recommendations for you. People say the perfume you wear reflects who you are, so I was very cautious when making this decision. And this is what I did a few months ago when I was trying to look for my perfect match. So I thought, as a data scientist, I should be able to answer the questions by using data science knowledge. So what I want to do is to build a recommender system to recommend perfumes to customers. I separate my customers into 3 tiers: new users, intermediate users, and perfume lovers. For the first 2 tiers, I will build a content-based recommender based on their answers to my questions. And for the 3rd tier perfume lovers, I will recommend based on their rating history. How do I get there? The process is I scrape data from the website, store them in MongoDB, and conducted feature engineering, modeling, and cross-validation. And now, after the model is finalized, I develop a web app, and then I deploy it onto AWS. Now it's running on AWS EC2. The data I got are 2 tables. Perfume data include features such as brand, theme, node, gender, and user rating data include users' rating, score, and user comments. The first model I built is a content-based recommender. So in order to gather more meaningful features, first I conducted topic modeling using M and LDA to user comments to extract features about consumers' feelings about each perfume. And then I end up with 12 topics from LDA. As you can see, here's a brief overview. Number 4 is describing a sexy, mature woman. And number 7 is describing a sweet young lady. And number 10 is describing a mature, reliable guy. So that's what I want. I add all these features to my perfume matrix, and then build a content-based recommender based on Jakarta similarity. The second model I built is collaborative filtering recommender. The baseline is predicted mean rating for everything. And I got the evaluation metric I use is root mean square error. So the baseline is 2.2, and then based on that, I built an item similarity model and as well as a font cascading model. The item-item similarity doesn't work so well because the matrix is too sparse. So I end up using a FunkSVD model with 14 latent features added regularization as my final model. And the final product is a web app. Actually, if you have a laptop, you can access through that URL. And on the homepage, I have 3 buttons, each of them targeting at one user group. So for new users, I will ask you a series of questions, like how do you want to feel when you are wearing perfumes? And based on your answers, I will provide personalized recommendations. And here's some Chinese text because I scraped the data from the Chinese website. And then for the intermediate users, I will ask what you liked before and then recommend based on similarity with the product. And then for the third tier, I will just recommend based on your rating history in my database. So for future work, in order to improve the quality of my content-based recommender, I need to get the price information of the perfume. And also, I want to explore where to back so that allow users to enter multiple perfumes and see, combine them together, what will I recommend. And also, I want to build an automatic data processing pipeline so that makes sure my data is not outdated. Thank you. My name is Kelly, and I'm happy to take any questions.
It's a very thorough project, so congratulations. The question that I have is not so much on the data science side, but a little bit on the engineering side. So so you built a very nice looking Flask app. How much time does it take you to predict, to give out a recommendation? And how will this app scale to, say, for example, 1 million users?
Oh, that's a good question. So right now, the prediction for each input is very fast. I think it's just after you input the perfume name or perfume ID, that the result will come right immediately. And for the scalability, I think right now my data set is about 20,000 rows. So if it scales to millions of rows, then I need to think about how that's gonna be, because that's a good question, but I haven't thought about the scalability yet.
So you tested this on people, right? And how did you measure their satisfaction?
Actually, one of my classmates wearing a perfume I recommended yesterday.
How satisfied are you, sir? Thumbs up? Thumbs up. I'll take that as a yes.
What if you were asking the same questions to perfume lovers, the questions with which you make a recommendation, content-based recommendation?
Yeah, actually, perfume lovers can also use these first 2 functions, but in addition to that, because I have their rating history, so I can look at what other users similar to them like and make recommendations based on other users. That's an additional feature for perfume lovers, but they can also use the first 2.
Yeah, and it would be a good way to feed your other algorithm, right? And help it learn more and more. If you were to ask the questions to perfume lovers as well, like in addition to their ratings.
Yeah, that's true. If I can store their data, then my model will become better and better.
And are the ratings timestamped?
The ratings are range from 2 to 10. Our scores, not timestamped.
Oh, okay. So you don't really know when exactly.
Yeah, yeah.
Thank you.
You made it again.
I know, I don't like being awkward, like banging into people when I'm not with them.
Hi, everybody. Thank you so much for attending today. Let's give a huge round of applause to all of these projects that we just had. So, happy hour is going to begin now. We actually have some beverages stationed right outside the door that are about to be brought in, and we'll have an additional snack drop shortly. So I encourage you to come up and and mingle with your fellow data scientists and say hi and hang out. Thank you so much for coming.
Yeah, I've already had